Greetings and welcome to this presentation on generalizability theory. My goal for this will be to present some concepts to help familiarize ourselves with the options that are available to us for estimating reliability. The content is mostly from this piece. It's Schout and Fleiss, 1979. And I put a link to the full text here, but I also hope to post the actual article on SharePoint. I'm going to go over the concepts that are more high level, but if you really want to get into the weeds, feel free to check out that original source. GT is a more flexible technique than CTT, classical test theory, and that is the primary paradigm that we've been working with up till now. And basically CTT, we have our true score plus our error equals the score that we observe. So it only breaks down the variability into those two pieces, true and error. GT does much more than that because it allows us to break up that error into multiple parts. So a lot of that error is systematic, so we can parse it out of the actual error, which residual by definition is non-systematic. So what part of our error is systematic that we can parse out and allow us to see more clearly the true standing of our individuals? When we do selection, we want to have that good ranking system that is reliable and trustworthy so that we are selecting the best people for the job. Now, generalizability theory uses this term generalization. Now, what does this mean? Well, Cronbach said a lot about this in his 1972 book, I believe, and I think he is the one who came up with GT originally. And yes, he is the same one who also gave us our inter-item consistency for reporting reliability of scales, our alpha. And he basically made this argument that any rating's usefulness really depends on the extent to which it allows us to generalize to a wider set of situations. So, for example, in order to reproduce any rating that a rater makes, we have to have access to a number of different facets, as Cronbach called it, or conditions, or sources of variance. So we would have to have access to, first of all, the target's actual standing on the construct, the applicant or whoever we're rating, their actual standing on conscientiousness, on the skill that we're evaluating. And then we need access to the rater's policy. A rater policy is like a rater main effect, and that is when my personal biases, my personal feelings or values come into the ratings. And this is normal, natural, and not always a bad thing. But it can, when we account for it, we're going to parse out the variance due to my bias, and that's going to be good for the overall model. So imagine that I approach the rating situation differently than another rater. I'm looking for different things. Different things are salient to me as I'm watching the target's behavior. And you may see this across us faculty. Even though we're all experts in the field, different things are salient to us when we look at your writing, for example. When we're judging your performance as students, you probably have noticed that we pick up different things that we focus on, that you can maybe improve, or things that we like that you're doing. And so you have noticed probably that they're slightly different, and even though we may in general agree on what constitutes a very excellent paper versus a poor paper, the various things that we tend to key in on are different. And so that is an example of my rater policy. I pick up on different things. Maybe I have certain biases, or maybe I'm in a bad mood on a certain day, and so compared with the other raters who are rating with me, I will be giving lower scores or higher scores because I just want to get it over with, whatever. So those are examples of rater bias or rater policy. Other ambient conditions that come into play in the rating situation, maybe time of day. That's important. If I want to reproduce a rating and all of the ratings occurred right before lunch or right after lunch, I will want to have the second rating also be at the same time as the prior rating if I were wanted to reproduce it. And reproducing is all about reliability and consistency. Maybe the type of rating form is different. Maybe one is confusing versus one is more clear. And so I'm not going to get the same ratings when I change the rating form, even if the, let's say the rating form is the same in content, but it is just different in usability. Maybe it's a different font or it's unclear in some other way. It's not formatted very well, and so that may confuse some people and they'll give different ratings for some reason. I don't know. These are just some things that I'm thinking about that are what Cronbach would call facets, and facets are simply characteristics that are impacting my ratings of somebody. So generalizability theory is all about collecting data on all those different facets, and then you're able to come up with a better picture of what's feeding into those ratings and what's impacting the ratings. And you saw some of this in the Sanchez-Levine 2012 article on task statements and how remember, raters of task statements weren't agreeing with each other and why that was, and they speculated on some of those things. And they used generalizability theory as that framework. So I encourage you, if you have a chance, to go back and at least skim that piece after listening to and digesting this presentation, and hopefully it will make more sense to you. Okay, so let's say we have an AC situation. AC in the context of selection typically means assessment center. Assessment center is a selection technique method that puts participants or applicants through a set of exercises, and for each exercise they are rated on at least a couple of dimensions. For example, leadership skill, clear communication. We'll just use those. And different exercises that they are put through, at least two of them, things like role play and leaderless group discussion, or they're making a group decision. And you put applicants in these situations and rate them. So they usually have multiple raters, and AC is a wonderful technique. It's however very costly in terms of time, training raters and getting applicants to come sit down with you for a few hours to do all of this. But they're often used for positions that require a lot of responsibility, and so they're high stakes, and therefore that justifies the cost. This is something that we're talking about in class that we eventually want to implement in our program, and hopefully we can in the future. So candidates' AC score is a function of the following facets, and these are not all-inclusive, but they're the main ones. So first we have inter-rater consistency, the rater policy issue. So as raters we come to the task with our own sets of things that are salient to us, things we look for, and you can, I think, do some damage control on this one with proper training. But the latest that I've seen is that it doesn't eliminate the problem. It may make it better, but raters still have their things. And so you have some of that, and some of it you can predict. So it's systematic variance. The second thing is dimension effects. Pardon me. So candidates have a certain standing on the construct that you're rating them on. And so across all the exercises, a good candidate should show fantastic leadership skills across all the exercises. And to the extent that they do, then they're probably going to be at the top of the list, and you'll want to select them. Exercise effects. So this is when people do better within the exercise. They just do well on all the dimensions within the exercise. So someone may perform better on the leaderless group discussion than they'll perform on the role play. And maybe they'll do better on the in-basket task than in the leaderless group discussion, or whatever. So exercise is just the situation that we put them in, the activity that they do, and then the dimensions we're rating within those exercises. So if there's consistency of scores within exercises, this is an issue because it's a monomethod bias. The exercise is simply there to allow people to display the trait. We'll talk more about this later in the class when we talk about ACs and the construct validity issues in those. But exercise effects are real, and so are dimension effects, and so we want to parse both of those out of the total variability in people's scores, AC scores at the end. And finally, we can have interactions among all of these different factors. So my policy may interact with an exercise, for example, such that I'm rating people differently in this one exercise based on my bias for whatever reason. And so you can have interactions among these different facets. Okay, so what is an interclass correlation coefficient? Well, the definition is it's a ratio of true score variance, or the variance we care about, usually relating to the person's true standing on the construct, to the sum of true variance plus error variance. Okay, so we have that sum on the denominator. So we have the error variance that we do not care about, the true variance that we do care about. And in generalizability theory, we get to decide how the error variance is parsed or is broken down. So with the example of an AC, we have the exercises. In this case, we have two. We have a role play and a group discussion. We have dimensions, 3 of them. We're rating people on assertiveness, organization skills, and leadership skills. And we have 3 raters. In this case, we have Dan, John, and Tiana. And incidentally, these are prior people who've taken the class, so I use this example for them as well. And then we have participants, and those are applicants. And we have, let's say, 30 of them that we need to rate. So if we were going to set this up in Excel, we have an example where we would have the raters entering their ratings of this person across these exercises. So let's say this is just for person 1. And so for applicant 1, we have these raters, 3 raters, and then we have the exercise, the role play, and dimension 1, 2, and 3. And remember, the dimensions were planning, leadership, emergence, and assertiveness, or whatever we decided they were. So those are going here for each of the exercises. Okay. So that's how we would set up a typical AC. Now, using ICCs to estimate rater reliability. So we want to understand in GT the extent to which average judges from a sample of 1 or more judges correlates with average judges from a population or universe of potential judges. Now we're going to talk about this in terms of a random effects model, which I will talk about here in a second, because whenever we're talking about generalizing to a population, that is implying a random effects. ICC, again, is the ratio of true score variance among individuals to the sum of the true score variance plus the random error variance. Okay, so the fixed versus random effects. Now, we generally in this program only talk about fixed effects ANOVAs, for example, and that is when we have 2 or 3 experimental conditions, or we're thinking about gender, or we're thinking about a classification of people like race, different categories. And fixed means that the categories in the study are the only ones of interest. So we are going to manipulate people's anxiety. One condition, we're going to make them very anxious, and the other condition, they're going to be very relaxed. That's a fixed effect. We're not trying to make generalizations beyond those 2 anxiety levels. Maybe we'll do 3. We'll do a low anxiety, medium, and high. And we don't want to extrapolate, even though I think we do in practice, we're not supposed to extrapolate beyond those 3 levels. So that's a fixed effects ANOVA. For a random effects ANOVA, it's a totally different concept, and it's this idea that your IV levels are actually sampled from a larger population of levels of your IV. So the example that comes to mind is like a drug. You have a certain range that you say, I'm going to test within this range of I don't know, I'm just going to pull something out of thin air here. 1 milliliter of the drug to 5, and let's say that is a safe amount of whatever it is, and everything in between. So you're going to do maybe by tenths. So you have this range that you're going to be sampling. So you're going to randomly select one of those levels, like 2.5 milliliters, and you are going to give the person that amount of the drug, and you're going to record their effect, the DV. And then you're going to do that many, many times for however many people you have in your sample, like 50 times. And then if you do that well, and you're actually randomly sampling from that population of that you've specified of levels of that drug, and that's your IV, then those results, whatever they say, like let's say the drug is found to be effective the more that you give, or the less that you give, whatever. Then you can make that generalization from the bottom of the range that you specified to the top. So that's a random effects. You can generalize to the population of sampled IV in this case. So you have to actually make sure that the facets or the different factors in your study are representative of the universe in order to generalize. So with the drug, you have to have actually randomly sampled. You couldn't just pick one non-randomly, decide, oh, maybe the drug, it seems like it's helping people the more I give, so I'm going to keep sampling from the top end. I'm going to give the 5 milliliters, the high end, all the time. You can't do that. You have to make sure that the sample that you employ is representative of the population to which you wish to generalize. And that's the idea behind this right here. So the judges, for example, that you use have to be representative of the universe of judges or the population of judges. So we want heterogeneity in levels of experience of the judges, their personalities, things like that, if we want to generalize back to that population of judges. Okay, so the linear model that we have here, I'm going to break down all of the different elements. So this Xij is Judge I's rating of the J target. Okay, target can be anything that we're rating, whether it's an applicant or a task statement or any other thing that we are assessing in the realm of selection. Okay, so it's a function of the following sources of variability. And I'm going to change that on the fly because I just noticed that was not spelled correctly. Okay, so mu, overall population, the mean of ratings. So this is the overall mean of the ratings, and that's noted by mu. And then we have Judge I mean ratings across all targets. Okay, so Judge I, that's the main effect for judge basically, and that's the AI term here. The BJ is the targets J standing in relation to the mean of all the other targets. Okay, so that's the one we usually really care about in selection. We care about this target standing on the focal construct of interest in comparison to everyone else. AB is an interaction between the two. So basically, Judge I departs from their usual rating schema when confronted with J target. I'm trying to think of an example of something like that. Maybe it's an attribute of the target that triggers the judge in a certain direction. So if the applicant is very friendly and the judge is someone who appreciates this person's warm demeanor, then you're going to have this interaction effect. Maybe the judge dislikes female applicants for whatever reason, or male applicants. And so that's an interaction that we can predict if we have enough targets and enough times that this judge is rating targets. We're going to see that judge's policy emerge and it's going to interact with this target. So if we have enough variability in target gender and we have enough ratings of this judge across targets, then we can maybe see that moderation happen. And then finally, the error term, the EIJ, is the variance that is unexplained. So it can include systematic variance, that other factors we could add, like time of day, and that would soak up some variance in this, or it's just random error that cannot be soaked up any further. It's totally random, meaning, remember, the very definition of random is we cannot predict it, so we don't know. We can't reproduce. So there is always going to be error in our model, right? That's just normal. So we have an example. Let's say 5 SMEs or judges are rating task statements for a particular job. They must rate the statement in terms of its importance to success on the job. So this task statement, how important is it that the incumbent do this thing if they want to be overall successful? Okay, so that's the idea there. So the ANOVA table, and this is given in the Shrout and Fleiss piece, we have the source of variance between targets, which we care about. The DF is going to be n, number of targets, minus 1. We have between judges. This is the judge's policy. Do some judges give higher ratings than others? And we're going to capture that variance. And in order to find this, we need to have all the same judges rating all the same targets over many targets in order to capture the judge's policy that way. So this represents, again, systematic or predictable variance in judges. And this isn't so important. The terminology that Shrout and Fleiss use is just there for you if you want it. And the DF is number of judges minus 1. And then finally, residual, the DF is here, and this is unsystematic variance that's not attributable to targets or judges. There may be an interaction between targets and judges, but if we don't model it, then we don't know if it's sitting here in the residual error, or if we can parse it out and put it up here and make that residual even smaller. So it could be totally random. It could be sporadic carelessness and ratings. Could be things like that that we can't model. Okay, so in GT, there's this terminology, a G study versus a D study. And I'm going to come back to this, so I want to make sure it's understood up front. A G study is a pilot study that establishes reliability estimates. So it's a study that you conduct beforehand, and I would say the most successful way, at least that I've done it in the past, is you want to train all of your raters to share an FOR, that's frame of reference, and have a shared understanding of what they're rating, and you want them to get them to agree as much as possible with each other on what constitutes good performance, not so good performance, and get their ratings as similar as possible. For the best case scenario, again, you want judges to overlap with targets. So if you have access to 5 judges or raters, have them rate a set of 20 or so. First, maybe have them rate 10 or so targets and make sure that they're starting to agree with each other, and get them to have a track record across many targets to get them to start agreeing. And then have them rate 25 to 30 targets, however many that you can spare, and have them completely overlap with the target. So that means if you have 5 judges, all 5 rate all the targets. That's what's the best procedure for a G study. And so look at your resources, like if you have 1,000 targets or whatever, and you're like, oh, I have 1,000 task statements I've got to rate. And if you're in HR, this may happen, especially if you work for the government. And you have SMEs that are in short supply. So let's say you have 3 SMEs available. If you can randomly select 50 of those task statements and get those SMEs to agree, have all 3 rate those 50 or however many that you need. And then you will have a good sample to calculate reliability estimates. And then your D study is where you have the remainder of your 1,000 task statements, and you can split those 3 up and have just one rater do each one. And then you're going to use the data, the reliability estimates from your G study and generalize it to the D study. Because if you just have one rater rate each of the 1,000 task statements, or the 9,950, however many, 1,000 minus 50, basically, you can't calculate reliability very well that way. You can't calculate inter-rate or anything if you just have one person rating each one. But you can take from the G study those estimates and generalize to the D study what your reliability estimates will be, because you're taking those three raters are your population of raters, and you're sampling one rater and you're extrapolating, okay, I've got one rater of the three. To what extent is this rater interchangeable with those other two so that I can have a good estimate for the inter-rater reliability, even though only one rater is rating each task statement, because you did your due diligence up here in the G study. All right, so the G study is the one where you're going to be very rigorous. You're going to have as many targets as possible raters as possible overlapping with your targets, and you're going to get some good estimates here to extrapolate to the D study. So that's why we do both. We're going to conduct both a G and a D study, and if you have many thousands of targets to rate, that's the best way to do it, and you don't sacrifice scientific rigor doing so. Okay, so with that in mind, Schoenflies talk about case 1, case 2, and case 3. Cases 1 and 2 are random effects ANOVAs. Case 2 is probably used more than case 1. So in this case, for our G study, we have each target rated by a different group of K judges. K is just a subset of judges that has been randomly picked from a population of judges. So imagine that you're a researcher and you want to see if content of applicants' Facebook pages predicts their future group performance. Their future job performance. So let's say you have to code 1,000 of these Facebook pages and you have to do a pretty thorough job with this. By the way, I don't recommend this kind of study unless you have very good IRB approval and you ask permission from people first before you look at their pages and make ratings. I just had to give that caveat. Okay, so you assign 10 trained raters to code 200 pages each, such that each page or target has 2 raters. But let's say that you can't have the same 2 raters on the same page. Okay, so no one page has the same 2 raters in the ratings. So you would run this, in this case, an ICC case 1, because you randomly divide the remaining pages among the 10 raters. So you're going to do a D study where you're going to have those 10 raters all branch out, and they're just going to do one page. Each page is going to have just one rater. So you want to generalize the reliability estimate from the G study to the D study. Okay, so just a couple of notes here. This is the proper way to denote an ICC. It's going to be, the first number is going to be the case. So this is case 1. It's a random effects. And unfortunately, since you couldn't overlap judges with targets, in this case, you didn't have enough resources maybe, so that like you had this subset of pages that you could have the same 2 raters rating each one, or the same 10 raters rating each one, in order to be able to get at the raters policy. So that's going to be in case 2 coming up. But you could not do that in this case, because in order to capture rater policy, you have to have the same 3 raters rating a set of targets in order to see that consistency. Rater 1 seems to approach it this way. Rater 2 seems to across everybody in comparison to the other raters. So you have to have that consistency in your setup. But let's say you didn't have the resources to do that. You have, and SMEs aren't always available. So if you're thinking about the selection context and trying to get SMEs and incumbents to rate, sometimes it's not possible. So case 1 is for those, admittedly unideal situations when you cannot have the same 2 raters or the same 3 or 4 raters rating multiple targets in order to capture that judge's main effect variance. Okay, so ICC 1 and then comma and then 1, this last number, is how many you're going to be averaging together to come up with the estimate. So in this case, it's only 1. So you're going to randomly divide the remaining pages among the 10 raters, such that each page has only one rater. Now, if you wanted to have 2 raters on each page and you were going to take the average of those 2 as the rating, that's going to be better because an average of 2 or 3 or 4 people all looking at the same page is going to be better than just one. It's like having more items on a scale than just one. That gives you a higher alpha. So inter-rater reliability in the ICCs are always going to be more if you have more than one in the second number. And I will show you that, and we'll do an example in SPSS as well. In my life, my professional life, I have never run a case 1, but I am letting you know it so that you know that it is possible when you are not able to have the same 3 raters rate all the targets, or the same 2 raters rate a bunch of targets. So all you need for the G study in case 1 is to have a group of K judges rating the targets, but they don't have to be the same, 2 or 3 people rating each one. Okay, so your population of raters is 10, and you're subsampling out of that 10 to do the D study, basically. All right, so if you were doing an average of 2 ratings or 3 ratings for the D study, you would put the 2 or the 3 here in the second number. So remember, I just put a reminder down here. G study is like a pilot study that establishes the reliability estimates, and the D study is the study to which you wish to generalize that reliability level that you got in the G study. Again, in this method, as I explained before, we cannot disentangle page content effects from judge effects. So if you want to know the judge's policy, it's not possible with this case. Case 1 does not parse that out. Case 1 is just between target effects and error. So in this case, it's very much like CTT in that respect. Okay, so case 2 I have done before. Case 2 is when you have a G study and you are able to overlap with the targets. So you have a subset of N targets that you're going to get your reliability estimates on, and you have 5 raters in the population, and each rater rates all of the targets. So you have a good estimate of both judge main effects, if you want to do judged by target interaction, and then you have the between target effects like you had in case 1. So you got it all in this case, and it's really great. And then for the D study, this is where the generalization comes in. You have this population of raters that you've trained them to share an FOR, they have a shared understanding of what they're doing, and then you're going to divide them up because of resource constraints. You're going to divide up the remaining targets randomly to a subset of those judges from the population. So you're going to randomly take these 100 task statements and assign them to 1 or 2 of the SMEs that are from that population. And in this case, in the random case 2, really what you're getting at is if these judges are interchangeable. Do they share a brain? I should type that under here. Do the raters share a brain? And I don't know if that'll help you remember, but it's this idea of interchangeability. So we'll talk more about this here coming up, but in order for the judges to share a brain, they have to agree on that scale of what comprises a 4 versus a 5. Let's say it's a scale from 1 to 5, and they're rating the targets, whatever they are. They have to have a shared mental model of what comprises a 5 versus a 4 versus a 3, 2, and 1. That means that you have to really train them well in the G study. Because it's not just a matter of their rank order being the same with targets, it's a matter of the absolute agreement of those judges. And so, and it has to be that way because you want to generalize this D study back to, or whatever reliability estimate you find in a G study, you want to generalize that to the D study. And so you're going to be taking that reliability estimate from the G study, and you are taking one rater out of the population of 5, however many you started with that you have trained, and you want to know if that one is properly representative of the 5. Because if you just have one person rating each task statement, you can't do a reliability estimate. You have to rely on what you found up here when you did the pilot study, and then generalize that to this one. I hope that makes sense. We'll talk more in class if necessary. So this is case 2. In this case, rater policy can be captured. So it's not just the between targets and then the error. We have we can parse it out into remember, judge main effects, target main effects, and then the interaction between rater and target. And again, the second number has to do with do you want 2 raters and use their average data, or are you going to do just one? 2 or 3 or however many. And remember, that will always give you a better estimate. So if you really need accuracy and reliability, then average at least 2 together. That's always a good idea. Okay, so case 3 is fixed, and this is analogous to the Chromebox alpha case, and that is when you have no generalization to a population. You have unlimited resources, apparently. So you're going to take all of your 3 raters, which is your population, and you're going to have them rate all of your targets, and that's it. So you don't have to worry about resource constraints where you're going to train them on part of the targets and then split up the raters for the remainder of the targets. So I gave an example here. Let's say you're estimating the reliability of 3 raters who will all be rating the role play assessment performance for police chief candidates. And again, there's no generalization needed here, so really this isn't a part of GT theory actually, but they do talk about it in the GT article because Trout and Fleiss, because it's a nice way to contrast the random and fixed effects. In this case, we don't care about judge interchangeability because we're not trying to extrapolate one judge back to the population of judges and if they share a brain. And in this case, we don't care if they share a brain because it's a fixed situation and they're all rating, so it doesn't matter. Okay, inter-rater consistency versus agreement. I made reference to this before, and remember, inter-rater consistency is that across targets, judges are consistent in their rank ordering of the target standing on the latent construct. So rater 1 has this ranking of the targets. Rater 2 has a similar ranking of the targets, but it doesn't have to be exact. So if rater 1 gave target 1 a 5 and rater 2 gave target 1 a 4, that is not such a big deal. They can differ in their absolute scores as long as the rank ordering is preserved. And I will show you that here visually in a second. Inter-rater agreement, that means that they have a very good idea. If absolute agreement, here's what it means. It means if rater 1 gave target 1 a 2, rater 2 also gives a 2. It can't deviate. Okay, so inter-rater agreement is much more stringent than consistency. ICC 2 is absolute agreement, and I think ICC 1 is as well, actually. So ICC, anything that's random entails absolute agreement. Okay, so inter-rater consistency versus agreement. Here's a visual of that. So this is consistency right here, and that is that the rank order among these targets is preserved. Even though there's a little bit of a disagreement here in terms of where target 2 actually stands. Okay, so rater 3 gave target 2 much lower rating than raters 1 and 2 did. But since the rank order is preserved, since target oh, I guess I should put target 1 here. So because target 1 and target 3 are still higher than target 2, then it's okay. None of these are switching rank orders. Okay, so if target 3 was down here for rater 1, then we have a lack of consistency. But here, everything is consistent, but not agree. There's not agreement. Does that make sense? So agreement's the more stringent criterion, and we have here some good consistency but lack of agreement. Here is some inconsistency. So we have target 2, rater 1 ranked target 2 higher than rater 2 did. And that wouldn't be a big deal. Oh, I'm sorry, it's the opposite. Rater 2 put target 2 higher. And what rater 2 did actually is basically the rank order is now out of sync because targets 1, oh, I don't know how the 1 went away there. So targets 1 and target 3 are higher than target 2 for rater 1, but they're lower than target 2 for rater 2. So the rank order was not preserved, and thus we have not only lack of agreement, but lack of consistency as well. Here we have agreement, and that means that for the most part, within error of me drawing this, we have rank order not only preserved, but also raters are pretty much in exact agreement about where exactly these targets stand on the construct. And so this agreement is very important for random effects, because random effects means those judges are interchangeable and they share a brain. So here, in consistency, they don't share a brain yet. They're getting there. But the rank order is preserved, but they don't share a brain in terms of where exactly these people fall, targets fall. But here, they do definitely share a brain. And so that is a good thing when we're trying to do random effects. Okay, so let's go over some examples. Choose your ICC. Scenario 1, we have a researcher who's doing some clinical ratings at a prison. They're trying to help prisoners, and they trained the raters to share, I should say the raters so you know. Okay, so after training the raters to share a frame of reference, she had all 10 of her research assistants rate 30 prisoners. So there's a subset of the prisoners. But there are an additional 150 prisoners to rate. So the researcher, after establishing with the G-study, divides the raters into 5 teams of 2. The prisoners will be randomly assigned to one of the 5 teams. The researcher will use the mean of the 2 raters' scores. What is the estimate of the reliability of these means? Well, which ICC would you run? Well, I put the answer here below the slide. And basically, you'd run an ICC 2-2 because for case 2, she had, remember, all 10 of her RAs rate the 30 prisoners. So she has an idea of rater policy now because there's that overlap with the raters and the targets. And so that means it's an ICC 2. And because she wants to average 2 of the rater scores, that is the second 2 there. Now, if she wanted to divide these 100 additional targets and have only 1 rater rate each one, then it would change to an ICC 2-1 in that case. And that's what I put right here so you know. Okay, scenario 2. Researcher has been doing clinical ratings in her prison research. Same context. She has 2 of her RAs rate prisoner 1, another 2 rate prisoner 2, and a different pair rate prisoner 3. Okay, so she had to do it that way. Maybe resources constrained her in that sense. And she wants to use the mean of the paired ratings in her analysis and wants to know the reliability of those averages. So in this case, it would be an ICC 1-2 because the ICC 1 lets us know that she wasn't able to have the same raters and all of her raters rate each of the targets. She had to just 2 of the, and they're different pairs every time rating the prisoners. And she wants to use the mean of the paired ratings. So that would be the 2 since it's pairs. But if she wanted 3 raters for each target, then it would be 3. And remember, her population is 10. Okay, so since the population is 10, we're doing a random effects ICC because we want to know If we picked Chris, let's say, as one of those 10, does Chris share a brain with the other raters enough so that we can make that generalization? Scenario 3, our researcher has had her funding cut and now can only afford 3 research assistants who will be doing all of her work for her study. She sends the RAs to the prison where they all rate all of the 200 prisoners that they need to rate. Okay, so in that case, what would the answer be? Oh, I forgot to put, she's going to use the average of 5. So I'm going to put, I'm sorry, my bad. It's ICC 3.3. Okay, so 3 is case 3, and I didn't put that she wanted to use the average. She will be using, oops. Okay, so she wants to average all 3 of her RA's scores for each of the prisoners, and so that would be an ICC 3.3. Now, I wanted to put a note here, use an ICC 3.1 if you wish to see how much reliability would diminish if you had to cut back to 1 rater. So moving forward, if you had to cut back to 1 rater, how much would your reliability diminish? I have never seen anyone use an ICC 3.1. Pardon me. I still think if you had to use 1 rater of the 3, you'd want to go to a random effects. So that one's a little bit fuzzy in my mind, that exact one. But just know that in a fixed effect situation, it is just like Chromebox Alpha in which raters are treated like items. So if you think about it that way, then it's a little bit easier, I think. Okay, so ICCs versus Pearson R. Pearson's R, or a correlation, just a basic bivariate correlation, is called an interclass correlation. And that means that we are correlating one construct with another, basically. So we're correlating IQ and GPA, height and weight, or whatever we're looking at. And so they're measuring different things. But for ICCs, and there are many types of them as we've gone over here, they measure correlations within a class or a category of things. So we have variables that are different measures of the same construct, and we're going to correlate all of those together. That would be an ICC. An ICC could be repeated measures on the same participant, like a test-retest reliability. So we're going to track people over time, and it's the same person. So that is an intra-class. It could be multiple people within the same group. So we have twin studies, we have students in a classroom, and we're going to correlate all of their scores on a same construct together. So GPA of students within a classroom, and we're going to get an estimate of how similar their GPAs are with each other. That's basically what a Chromebox Alpha does with items. We're taking all possible correlations and taking their average among the items. So taking all bivariate correlations with each item with another item and then taking the average. It could be multiple ratings per target. So it could be 5 raters all rating the same target. We're going to correlate all those with each other to try to get some kind of reliability estimate, basically. So ICCs are really important and they're widely used. You'll see them in research, you'll see them in journals, and they provide the basis of multi-level modeling, actually. So you will calculate these when you start to learn about MLM, I think later this quarter for most of you, when you take stats. Okay, so in review, just some general concepts to know. First, domain sampling theory. I just wanted to, it doesn't really fit exactly with this presentation, but I want you to know what it is. It's when a measurement tool is created by representative sampling from an infinite number of items that fully comprise the construct domain. So it is again, very theoretical. You cannot actually do this, but in theory, that's what we want to strive for, is a representative sampling of a universe of possible items. So it's this idea of, is my test representative of the population? So in that sense, it's very close to what we're discussing here. Is the test that I'm giving you for this class, is it representative of the content domain? Can you generalize a score on the test that I give you to the score that you would have gotten if you had gotten the whole population, which is not possible, but that's the thinking behind it, is that it's adequately generalizable and accurately reflective of the whole population. So again, CTT, remember, is the observed score as a function of true standing on the construct plus error, but GT divides that residual variance further into multiple parts. And this is especially relevant for selection research, as I said, when we have multiple judges, often rating multiple targets, whatever those things are. Okay, so I wanted to show you an example of what this looks like when you calculate it out. And this data is presented in Shroud and Fleiss, and the actual raw data is given here. And again, these are the names of prior students in the class as raters. And then there's a document also on SharePoint titled ICC descriptions. And this is a document that breaks down the type of ICC and a description of what it is, and the sources of variance that are estimated, which I've already talked about, and then the ANOVA term and the SPSS output that you want to look at, and the different coefficients that are given. This little symbol is called rho, and rho is the ICC estimate for the population. So that's what that is. Nothing, I didn't mean to scare you there by this, no harm meant by this symbol. It's just and remember, rho is the population equivalent of R, basically. I'm trying to think of what the journals use as far as an ICC, the symbol for it. I've seen rho before, and I've seen, I think RW, like within, R within, to try to capture that idea of within class correlations. But anyway, I don't want to digress here into the minutia of the notation. Pardon me. All right, so I forgot what these represent here, the 3, then the 2, and the 4. I'm just going to delete these off. I don't want them to confuse us. Thank you for putting up with my editing on the fly. All right, so I'm going to show you how to come to these numbers from SPSS. And basically, if you hadn't caught this already, just to recap, ICCs can be run on they're run on the same data and give totally different results, depending on the assumptions that you're making, basically. So you're making different assumptions based on the same exact data. So in this case, I have my participants, and they've rated each of these targets, and their ratings are given here. Okay, so this is the target, and this is just a nominal variable. It's just a target number, and then the raters' scores are beneath. So I'm going to first do a case 1, and I'm sorry, I'm bopping all over the place here. Scale and then reliability analysis. I'm going to do a reset because so this is what it should look like when you do it. And what you do is you take all your raters and put them over and treat them as items. So treating the raters as items is a necessary thing to do sometimes. And then click Statistics, and you're going to click the ICC option. And remember, we have a one-way random as our case 1, and over here, typically there's something to click here, but in the one-way random, it doesn't matter. So click Continue and OK. And in this case, it gives us the Chromebox alpha, so we have it, but we don't want to look there. We want to look down here actually. And for single measures versus average measures, so if we were going to average all of the 4 people together, the 4 raters, I think there are 4, right? Yes, there are 4 raters. If we were going to average them all together, then we would have this right here, and we'd have an ICC of 0.443. And note that that is small in comparison to our alpha, what we would expect for an alpha, which is 0.7 or above, or 0.8 or above, depending on who you ask. Remember, random effects are going to get smaller because we need that absolute agreement, because we're extrapolating results back to the population. And so look at the single measures, that's even smaller. And so when people see an inter-rater of 1.66, that bothers them. So you have to explain to your reviewers, if you are publishing a study, that this is a random effects and absolute agreement is going to always yield a smaller estimate than your average effects, which is a little bit better. And I'm looking at the raters. Let's look and see. And as far as absolute agreement, they do not have good absolute agreement. So this is a case where your raters not only have to be consistent, but they have to also be as similar as possible on their marks. So target 2 all the way from a 1 to a 6. They should be almost all the same in order to get high absolute agreement. So I'm not surprised that that one is as low as it is when you look at it. 0.166, and then even this one is low, but if you do average measures, if you're averaging them all together, it does improve it significantly. Okay, so maybe there's some rater policy stuff we're not capturing too. So remember, case 1 doesn't allow us to look at rater policies, so that's all going into the error term, making this tiny anyway. So case 2 should give us some higher estimates than what we get with case 1. Case 1 is always going to be very low. So I don't recommend using case 1 unless you oh, here's the article, by the way. Accidentally clicked here. Interclass correlations, uses in assessing rater reliability by Shaw and Fleiss. This is a very classic piece. I would say allow yourself some time if you're going to read it. I've read it many times and I get something new out of it every time. Okay, pardon my clicking. I'm going to analyze now and going to show you the case 2. Okay, so case 2, are the judges interchangeable? We want to know. So scale and reliability analysis, and we're going to go to stats, and we're going to do the two-way random, and that is case 2. Two-way random, and we want to do absolute agreement for two-way random because for random effects, I don't think it is appropriate to do consistency actually. It's most appropriate to do absolute agreement. So let's say okay. And we have for single measures, that's if we have just select one out of that mix, we have a 2.9 for reliability estimate. But if we do an average, a 0.62. And note that those are quite a bit higher than these two estimates were. So if at all possible, when you're creating your G study or setting that up, make sure that you train your people to have absolute agreement with each other, because that's really going to matter in terms of these numbers over here. Okay, finally, so the ICC 3 is, remember, the same as Chromebox Alpha, and so you can either run a Chromebox Alpha in the normal way, or you can get it by this as well. Two-way mixed ANOVA is the way that you would, let's see here, two-way mixed instead of two-way random. Okay, so that's two-way mixed is the same as alpha. And in this case, we're going for consistency. Because remember that our Chromebox Alpha only cares about consistency, not absolute agreement, because we're not trying to extrapolate from the population to what the raters are doing and vice versa. We're not trying to take one rater out of the population and see if they share a brain with the other raters. And there we have a much higher average, ICCs, and the average measures is the same as Chromebox Alpha. And again, for the single measures, I'm not sure when you'd use this, only in the case where you're trying to see if you were down to one rater, what would it be in the hypothetical. That's the only thing I can think of that you would use this. And again, I think you'd probably want to revert back to the random if you were going to do that. Okay, so that was probably a little more detail than you were bargaining for, but that is the basic idea behind GT. And so again, the highlights to know, the important points are this last slide, of course, that kind of wraps everything up. The difference between inter-rater agreement versus consistency, that's important, and hopefully this visual was helpful for clearing that up. And the understanding of how this ANOVA breaks down in terms of what constitutes between target variance versus between judges variance, and then the interaction. What does that look like? And I think that's about it. So we can talk more in class as well. You can ask me questions about this. Thank you for paying attention, and in a nutshell, and as simple as I could explain it, this is generalizability theory. Thank you, and I'll see you in class.